Hi guys, hi everyone. Welcome everyone who is watching live and everyone who will be watching later on the recording. Today we'll go through from scratch how you can download or obtain ready PyTorch model, then how you can profile it, what you can do to optimize it, how you can utilize ONNX format to later put it inside of JavaScript code and run it on your website using webcam as your data stream. Okay, so let's jump straight in. Here we have the repository I will be using today, and that's the one I was displaying on the video that was previously featured on our channel. So this is implementation of fast neural style transfer, which was proposed quite some time ago. It's nothing new. That's not really the point of this today presentation. We're just going to utilize this as it achieves a very nice visual effect, and yeah, it's fun. So let's go. The models can be downloaded from here. There's a zip archive that you can download. I did it already before, so we don't have to wait for that. What else you need to have is this file here, which is the architecture of the model. So I will give a brief explanation of what's happening here. The model is fairly straightforward. It consists of a couple of layers which are doing downsampling, so they're reducing the input size of our image. This is downsizing by factor of 4. So if our input image is 640 by 480, the resulting downsize would be 160 by 120. Okay, what else? With each layer, we are increasing number of channels. Channels are, for those that are not aware, for a regular stream, we have either 1, 3, or maybe even 4 channels. This can be grayscale. In that case, we have just 1. RGB, then it's 3, 1 for green, 1 for red, 1 for blue. And 4 if we add the alpha channel as well, so RGBA. Okay, so we are starting with 3 channels, then going to 32, 64, 128, and that's the final size of our embedded size. Then we are processing using 5 blocks, which are called residual blocks. I will describe them briefly as well. And then we are doing the same in reverse, so basically upscaling back to the original size with those 4 layers. What else? We are using ReLU activation. This is rectified linear unit, very common activation, the simple one that's available. This one is necessary because without any nonlinear activations inside your neural network, no matter how deep you make it, it always can be reduced to just single layer, because any number of linear functions can be reduced to just one single linear function at the end. So basically, we are achieving nothing, and we are wasting a lot of computing power if we don't add any nonlinear activations. So authors, in this case, use the rectified linear unit. Here we have our forward pass, which is just going through each of the layers that are written above, and that's everything. Very straightforward. Okay, so what's a residual block? We can scroll down a bit, and here we can see what's inside of that. So residual blocks were proposed even earlier than style transfer. I think it was 2015. What they utilize is what's called a skip connection. So basically, we are at the start of the residual block. We are copying our input to the two parts. One part we are passing through some layers and doing some transformations on those, and the other we are just passing straight through and adding at the end. So here we can see that at the start the X is duplicated. One copy is passing straight through to the addition at the bottom, and the other is going through a layer, then activation function, and another layer. In this case, those layers are just convolution layers. And the ReLU is the same rectified linear unit that I showed before. And then we are adding output of this transformation here to the original input value, and we are passing it for the further processing. What this achieves is that it allows the network to basically, in the worst case scenario, if for some reason the additional depth is not required, it is very easy for the network to learn just identity functions. So basically do nothing. How you can do that is just imagine if instead of those weight layers, if all weights are equal to 0. What happens then is after processing, the output of those layers is still equal to 0, and then we are doing just a simple addition. So 0 plus x is x. So that's one thing that residual blocks achieve. So basically they cannot hurt performance of our network. They can only improve it. And the other thing that they do is because of the nature of how neural networks are optimized and how they are learning their weights, which is using gradient descent, there's a thing called diminishing gradient. So basically, if you have a very deep network, you can imagine the gradient is what's called a backward pass. So it's going from the output back up the stream up to the first layer, so to the input layer. And with each step, the effects of the layers that they have on the input, because they are farther away from the input, grows smaller and smaller. And so the gradients grow smaller and smaller, and we are making very little changes to those layers, which makes basically the training of very deep networks impossible. What this achieves, so the residual block, because we added those skip connections, we basically significantly reduce the longest path that we are that is available in our computational graph. So basically, to summarize, what this block achieves is we can build deeper networks with the same performance, and we can train them faster. So it seems like a win-win situation. Okay, so going back to our model, that's the residual block. And was one last thing that I have to mention is the upsample conv layer. So the convolutions basically utilize rectangular kernel that is being moved over the input. So basically, if we have our input is 2D array, then we are taking our kernel, which could be which is very common size 3x3, and we are sliding it by on every possible rectangle of 3x3 of our input, and we are just doing multiplications and then additions, and that's our resulting feature map, what's called. So what's interesting about that is basically you can think of this, that we are basically gathering information from some region of our of input data and concentrating it into one single value. So this seems quite counterintuitive if you want to upsample, so make the image larger, because well, we are like doing like magnifying glass effect on the input. So there are two solutions about that we can use. One is to basically flip it on its head, so just do the same but in reverse. So we are like basically instead of the cone being smaller at the output, it's larger. And this is one of the solutions that you can use, and you can do upsampling like that, but it leads to very nasty artifacts on the output. What authors proposed here is doing just normal convolution and then doing upsampling like interpolation. So simplest possible way to upsample something. So basically the upsampling enlarges the image, and then convolutions try to smoothen it out and make it look nice and pretty for us at the end. Okay, so that's enough talking about that, and we can go to our code. So here's my prepared file that I just showed, which is the transformer net, as they called it. And here in models, I have downloaded the mosaic.pth file. So what we can do with that? Let me go back to my transformer. Okay, so what we need to do is we need to load our model here. This is, there's nothing happening here, to be honest. What we are not, what's different than just loading the model like you usually would, is we are not copying the running values from normalization layers in between. So yeah, just skipping some values that are not necessary for inference and are only used during training. So this is loading our model. And here we have a profiler. So let's load the model. Okay, so the model loaded, and here we can see what's happening on each layer. I will talk about that in a short second. What else we want to do is we want to export it to our ONNX format. Okay, so just uncomment this. What do we have here? So basically this is like box standard version of exporting Torch to ONNX. As you can see, ONNX is a built-in library for Torch. And what we are passing in, we have to provide the PyTorch model. Then we are providing input, because for exporting, we have to provide sample input with basically what's needed is sizes for ONNX to know like what's the order of layers that are called in. Then we are passing the name of the model, offset version, which doesn't really make a huge difference right now. This flag is whether we want to save just the shape of the model, or also we want to export the parameters. So of course we do want to save parameters as well. Input names and output names, that's that's quite obvious what that does. And finally dynamic access. So the last one is needed if you want to later change the input size for our model, which is exported. If we don't do that, it is basically frozen to just one single output size, and we cannot change it later. We have to do the export again. So we are just setting the second to last and the last channel to be dynamic size. So this is called width and height. So as expected, we want to be able to change width and height of our model. Okay. So if we do that, run the script now. One small hiccup. Okay, and here is our exported model. We cannot open it in text editor, but yeah, it's not really something we can read. But Yeah, you can confirm that there's something in it. Okay. So now that we have our ONNX exported model, let's see how we can put it inside our JavaScript code and run it on our website. So for that, let's refer to our ONNX runtime JavaScript API documentation. That's what we'll be using today, and we'll be using WebAssembly as our backend to basically do all of the computations on our model. So we won't be using graphics card. We will be using only CPU. Okay. So let's get started. So I have just a couple of files prepared beforehand. One is just webpack config, which is basically the same as you can see here. This is ONNX runtime inference examples. The other that I have prepared is just the simplest possible index.html, which is basically including the ONNX runtime library inside of the script. Okay, so let's go to the code. So here's our HTML. So we are importing the ONNX runtime minimal build, as well as the build bundle min.js file, which that's what we want our webpack for. Here's the webpack config. Basically nothing here. And let's go with coding. Okay, so how this is going to work is, to give a quick rundown, we will be taking input from our webcam, then putting in with video element and drawing it onto a canvas which won't be attached to our DOM because we don't want to see that, or well, maybe we can add it, but if you want to see only the processed output, there's no need for that. So we'll be putting on the detached canvas element, then from that we'll be taking the data, putting it inside of a ONNX runtime tensor, putting it inside, passing it through our model, and then finally converting it back to the canvas format and displaying it on our page. So we'll be doing everything frame by frame. Okay, so what we need is our canvas that we'll be displaying things on. So that's something that we have to add inside our HTML. So let's do that now. And let's give it ID, and that's the display canvas. Okay. Apart from that, we want to set width of that, and let's put it for 640, and height to 480. This is those values are not random. This is the resolution of the webcam. It's by default. So we'll be using aspect ratio 1:1. We won't be scaling. Not aspect ratio, but we won't be scaling down or up anything from our webcam onto the canvas. Okay, so that's our canvas. Let's go back to our JavaScript code, get that, and now, as I mentioned before, we have to create two elements. One is video. Oops. And the other one being our canvas that will be our hidden working canvas. Okay. Apart from that, we want to take context from this canvas. This is used to draw anything on canvas. Okay, so we are just obtaining that, and we also need to set width and height of this canvas we just created, which will be the same as of our display canvas. Okay, so now that that's done, let's go to our main function that will start everything. So just we will call it onload. And what we want to do is, well, one thing is want to create session here for the ONNX inference. And also we want to obtain access to our webcam. So let's do the webcam first. Okay, and we have to pass what we want. So we want video, and what we don't want is audio. Well, we won't be needing that, so let's put it to false. And then on success we'll get stream object, which we have to process, and on failure, well, just some error, and let's put it to console error. Okay, so error handling, very rudimentary error handling is done. Now we can go to our main function. So let's attach the stream to our video, so that it's basically we can take the frames from inside from within the video, and let's set it to play. What else? Let's take the width and height of our stream. Okay, so this is also self-explanatory. We are just saving the dimensions in case we want to use a different webcam. We have them ready and not hard-coded. And after that, we just we are calling a different function that we need to now write. Okay, so let's go with this function. This will need to have an async function. No arguments for that. And now what we need to do is we need to obtain our input data. So this will be the input tensor for our inference session. So how we can do that? Ort. So this is a fun function which we found out inside of the GitHub repository. I think this and the function that's converting from canvas format into from a tensor format to canvas format is also not really listed inside of the documentation. So if we go back here to our documentation, we can see that there's tensor. I'm sorry, this interface. So we can see the function to image data exists here, which is listed, but there's no mentioning of conversion into the other direction. So where we can find that? We have to go inside ONNX runtime GitHub repository and inside tensor factory implement TypeScript file. We can scroll down and see that there is this mysterious function called tensor from image, which is very promising for our use case, and turns out it's the exact one that we want. And we can see here that it is used inside of tensor from image function. So we can use that. So there's tensor from image, and what we need to pass here is our image data. So get image data. Image data requires information on basically the coordinates that we want to extract the data from. So this one will be canvas width and canvas height. Okay. We need to also put some data onto the canvas because, well, right now it's just empty. And for that we are going to use the video element that we have right here. So let's take canvas context, draw image, and first source of our data, which is the video, and now some boring numbers, which is the coordinates that we want from which coordinates we want to extract data, and coordinates that we want to display the data at. So there are 8 numbers that we need to pass. And here the width, as well as window height. Okay, and now again 0, 0, which is the beginning of the coordinates, and here the canvas width and canvas height. Okay, that should be done. So here, oh right, this is asynchronous function, so let's put await there. Okay, I need to also create our ONNX inference session, which I forgot to do before, so let's go back here and again asynchronous function. Nice. So here into our inference session, okay, good points. This needs to be asynchronous, not here. No, okay, never mind. I don't need async here, my bad. Okay, so I just create. We need 2 arguments for that. One is model path, so let's define that here. And the other being our options. So let's see what options we can include inside the ONNX runtime session. So let's hop right in back here, and here we need inference session, and let's see. Inference session factory. My bad. And here session options, and there is a vast array of options that we can choose from. As I said before, we will be using just WebAssembly today, and for that what we need to provide is execution providers. That would be WASM, which is the WebAssembly shorthand. And what else? We can put some other, like execution mode, for it to be sequential or parallel, or some other options I will mention shortly. Okay, so let's go back in. So as I said, we need execution providers, which is the most important one. For some reason this is array, although only one value is supported at once, and if you pass more it will crash, but yep, that's what it is. And we are passing it here, and we have the session, and let's put the session into the window so we can access it. It's our other functions. Okay, so now let's get our output from our session. So here one thing worth mentioning is that the name of the output variable, as well as the input key inside of the arguments we are passing inside the our ONNX inference session, are the same names that we put when we were exporting our model right here. So the input and the output right there. So just keep that in mind. If you change it to something else, you need to change it here as well. Okay, that's also asynchronous because we need to. It will take some time to do the processing on our CPU. Okay, and finally, we are taking our display canvas context from this again, and there's this function put image data, and here we want to take our output, which is of type ONNX runtime tensor, and convert it to our to image data. So for that, we need to do this. Okay. Another thing worth to keep in mind is that image data by default returns values. It basically tries to normalize it by default by multiplying it by 255. So unless your model output is between 0 and 1, you need to keep that in mind and change it, because otherwise, well, you will get basically white screen as your output because of the overflow. So we will change this here. We want RGB format, and we want to normalize it by basically not normalizing it at all. So just multiply by 1. Okay, and I think this should be working. And of course, we need to put the coordinates of the upper left corner of the data we want to, like the beginning of our rectangle that we will be displaying onto the canvas. And after that, we need to basically loop again the same things. So that's where the request animation frame comes in handy. It basically tells to run the function on the next repaint of the screen. So yeah, there's no downtime. It basically runs instantly. Okay, so let's see if this works. So what we need to do is run our webpack as well as our server. So here we can see the server is set to run on 00 and port 8000. So let's go there and see what we have. Okay. Another thing worth mentioning is that in Chrome, unless you're on HTTPS site, it will not allow you to use your webcam because of security reasons. So even if you're on localhost, you cannot get it. So here we have null properties with. Okay, so let's see where we can have that. I think this might be the culprit. Oh. Okay, yeah, there's the typo. Okay, let's see now. Okay, there's one more error. Let's quickly look for that. So it's complaining session run is not a function. Why is that? Oh, so that is a promise, so let's await it. Okay, so a little bit more. Oh, yeah, and one last thing we forgot to do is setting our model path. So here's our mosaic.ONNX model. So let's put it inside our build directory, and let's put it here. Oh, actually it's /build. And let's cross our fingers and hope everything works now. There are no errors so far, so it looks good. You can see the webcam is turned on. And something is happening. Okay, so yeah, right now this doesn't look like a video of any sort. It's, if I were to guess, about 1 frame per 3-4 seconds. So that's not what we want. Let's see what we can do. So I mentioned before that we have some inference session options that we can play around with, and let's check that. So one thing is execution mode. That's something we want. We want it to run in parallel. So let's add that right here. Okay, what else? So execution providers, that's set. And yeah, graph optimization levels, yeah, of course, why not? Any optimization is good. This all doesn't achieve really a lot of performance boost, as we will see shortly. And yeah, another thing we need to set is, although it seems like those are a lot of options that we can set for our inference session. Those are just like general ones, and we want to set some WebAssembly specific options. So for that, we need to refer to env object, and then inside WASM namespace, we can see that we have another which is simmed, which is important, but that one is turned on by default. And also what we have is number of threads. So that's something we are very interested in. Another thing that's keep in mind to set, or maybe not, depending what you want, is to set the proxy to true. So basically what it does is decouples the inference from our main worker thread for the website. And for example, if you want to at the same time update some other objects on the document, unless you do that, there can be some problems with that. We had that happen before, and that's how we found out that the proxy setting is very important. So let's do those changes now. Proxy we are setting to true, and the other thing we are doing is the number of threads, and let's put it to 4. Okay, so let's see if we are doing any better right now. And here, if you want to check number of threads running inside your browser in Chrome, what you have is inside Sources tab in your developer tools, there is this threads dropdown. So there's one thing that you might find interesting. So although we set the number of threads to 4, we can still see that there's just one thread apart from the main thread, which is the one that we achieved by setting the proxy to true. So if the proxy was false, we have only the main thread. So why is that? Why are we achieving only one thread and not getting any more, even though we are trying to set the configuration up to 4 threads? So this is another interesting thing. Because of some Spectre attacks that happened in the past, as you may be aware of, the short array buffer that's used for multi-threading inside of ONNX runtime is not enabled unless you set some course specific options. So yeah, as you can see here, 2 headers need to be set for cross origin to isolate our site. So unless that's enabled, we cannot be using the short array buffer, and so we won't be getting any more than 1 core, because ONNX is, well, not trying to waste threads. So for that, let's go back to our server file, which, yeah, there's, well, nothing here, just serves those files. And let's set header, and 1 is that, and we want to the value same origin, and the other one, let's copy that as well to require corp. Okay, and let's see if we have any luck this time. We need to restart our server. It doesn't take very long. Let's refresh the site. It's still loading. But what worries me is we can still see only one thread, which is not what we wanted. So possibly a little bit more debugging is required right now. Oh. So I made a mistake. Is there a typo here that we can see? Oh, it's not inside of the error that we want to send it. It's right here. So that makes sense. And voila, you can see 4 threads are live, and that should significantly speed up our example. So another thing you might be tempted to do is to measure the performance of your inference basically program. So one thing that comes to mind how you can do that is by logging times or timestamps to console. So let's do that, and let's see why it's not a good idea. So going back to our main.js file, on each let's remember our start time, and after that let's basically compare it to our current time and see how long it took for a single frame to render. Okay, so that looks good. Let's refresh our page. Okay, so yeah, 1.6 seconds per frame. But that's not quite true, because once we turn off the console on the website, we can wait a bit. What happens is that whenever you open developer tools inside Chrome browser, it starts profiling WebAssembly code, and basically it slows it down by half. So as you can see, once we shut down the console for a while, we can see that it's basically twice as fast. So unless you want to basically print it all the time to your console and then go back and see and so on, this is not the best idea. But don't try to don't take those values very seriously, because they are just erroneous. So we can just add quickly live FPS counter. So let's do it like that. Let's create array with 5 values and fill it with performance now. So that's our initial values for our timestamps. We'll be tracking average frame rate of our last 5 frames, so it doesn't flicker as much and goes up and down because of our loads on our computer. And then on each render, what we need to do is we need to shift it back. Then we need to set our last value to performance now. And then we can log. Well, as I said, console logging is not the best idea, so let's actually get a live counter underneath our canvas. So basically we'll do a div here, we call that FPS, and let's set 0 as the initial value. And now let's update that, get element by ID, FPS, and set the inner HTML of that to 1000 divided by the difference that it took, the time it took for our last 5 frames to render. So this is window timestamps, the last value minus the first value, and then we need to time it by 5 because we are this gives us the number of frames, the time it took for 5 frames. So we are dividing it by multiplication of 5. So by multiplying it, we are getting back how many frames per second, not batches of 5 per second. So that's what we want, and we can leave we cannot leave that because we erased something. And let's refresh, close the console, and we are expecting slightly above 1 frame per second, as we saw before. We are achieving about 800 milliseconds per frame, so that's more than 1 frame per second. But that's still very low. So let's see what's really the bottleneck here and how we can speed it up even more. So for that, we'll be going back to our profiling output that I mentioned before. So let's copy that over to our window so we can better see what's happening. Okay. So as you can see here, at the start, what's here? Those are convolution layers. Those MKLDNN convolution. So that's convolution layers. There are some upsample layers that I mentioned before that are in the upsample stage of our network. And here we can see what's taking the most time. So what's interesting is that although the first entry is taking 1/3 of our CPU time, there are 10 calls of that. So actually it's not that much. It's 3% per 1 call. But what's very interesting is that the following 2 layers, one is occupying 14% and the other over 10%. And those are both just a single layers that we have in our network. So if we want to significantly speed it up, speed the performance and increase the performance of our network, we need to somehow remove those bottlenecks. So what's causing those bottlenecks? First thing is that we can see here, those are the input sizes. So those 2 layers, judging by the input size, we can identify which of the layers inside our model were causing that. So that's the first conv layer and the second conv layer. So what's happening here is that both those layers, on the input, they're getting very large, like very big dimensions of our input data. So that's 640 by 480. So that's quite large, and that's basically the speed is proportional to the square root of not square root, but the square of the dimensions. So those are quite big. So the easiest way we can speed it up is by making it slightly smaller. So let's see what happens if we change the input to 240 by 180. So okay, let's see now. And there it is. We can see it's much smaller. We can change it using CSS to be to appear larger on our screen, but the performance stays the same. And now we are achieving very nice, almost 10 frames per second. We can even speed it up by providing it more cores. So right now it's running on 4. So we can bump it up to 6, which is maximum on my machine. Anymore is not getting any more performance. So we can see 12 frames per second. So that's one thing that we can do to optimize it. But as you can see, the quality of our outputs is much worse because we are basically losing a lot of detail by downscaling it, then changing style, and then trying upsampling it to our desired output. So what else we can do? So let's go back to our profiling output. And one thing that we can try is to see if we can eliminate some of those layers. So, for example, is it necessary for us that we have to have one layer that is not doing any downsampling and then doing downsampling on those 2 layers? it turns out it's not really that necessary. It certainly improves the visual clarity of the output, but it's not strictly necessary. So that's why we tried to learn a smaller, different model. And that model is available here, the architecture. So basically what we changed, instead of 3 layers that are doing the downsampling, we changed it to 2. So every layer is actually doing downsampling, as opposed to before, where first layer was not really making the input any smaller, only making it wider, so changing from 3 channels to 32 channels, so it's 10-fold increase in amount of data that's being passed through the model. So we eliminated the first one, and then what we do is analogous thing on the upsampling, which is removing of one of the convolution layers. Then another thing that we can do is, if you remember before from the start, residual blocks are useful for speeding up the training, as well as not hurting performance of our network when we are making it much deeper. What we are doing this here is quite the opposite. So we are not doing it, making our network deeper, we are making it much shallower. So we guess that it is not really that necessary for us to keep the residual connections, and therefore we could significantly reduce the number of layers that are happening on the smaller size of our network. So looking here, if we load this model, the modified model, and we'll call that, we have to, I have it of course pre-trained because it takes a couple of hours to train the model from scratch, so that's not very feasible for now. That's why we have the models here already prepared. As you can see, there are some more, but that's for later. And that's our mosaic compressed model loaded. And now for the export, let's also change the name. And let's run it now and see what our profiling shows now. So here we can see that the percentages changed. Let's again take it from this small window and put it into larger one. So again, we have convolution layers here, and we can see the input shapes. So that is in fact the same initial layer that was happening before, and it's still taking a lot of time, but it's now taking relatively more time, but only 57 milliseconds, as opposed to before. We can see it took 358 milliseconds. This is because of this value here. It is our number of channels is greatly reduced from 32 channels to just 12. So basically 1/3 of that. Okay, so that's our model. As I said, it's much smaller. Should be much nimbler and lighter on our CPU. So let's put it inside our build network and see how it goes and how it performs. So we called it mosaic _2, and here we can see this just crazy numbers above 70, so significant speed up. But let's bump up the visual clarity a bit by scaling it back up. And here we can see that we are achieving above 20 frames per second with the same model on the same architecture, on the same CPU. And although the image quality is a bit lower, I think, in my opinion at least, the fluidness makes up for that very significantly, because now we can see that we can actually call that a video instead of just some very rarely refreshing photographs. Yeah, so as you can see, this is 20-25 frames per second. Turns out we can improve it even more. This is done algorithmically by removing one random channel from each layer, then trying to see which channel actually impacts the performance, has the smallest impact on the performance of our network, then excluding it and retraining our network without some channels. So that's why we have some more here. We can see, let's take a different, and that would be the last thing that I will show, because we are running, getting closer to our stream. So here let's get the underscore 36 model. And as I said before, this model is reduced. Those values here, those arrays, are the modifications to the layers, the subsequent layers, and how much we are reducing the number of channels on those layers. So we are using the 36. This one is here, which I already prepared. And this is the number of channels that we are reducing. So from 24 channels on the inner layers, we are reducing it back down to 9, 10 layers. So they are very, very small. Okay, so let's export that and see if we are getting any significant improvement. Okay, so again we can look at our profiling results. So here again, the same first layer is very heavy, very computationally intensive and demanding for our CPU, so it's still occupying over half of the time, and there's not much we can do in this way about it. But we are reducing the inference time even more. So let's see how well this performs. And let's go here, change it to our 36 model, and refresh. And we can see we are getting up to 30 frames. It's very jumpy. We can actually, what we can do to make it much more stable, let's change it to 25 here. This would give us much more stable results, so we can actually see what's happening. Okay, so those are the basic ways you can use ONNX runtime and how you can profile your model with PyTorch profiler, how you can detect bottlenecks, and how you can figure out if you can make the model much more concise and perform much better. So we will be I hope that this stream was interesting and helpful to you if you are interested in any of this, and I'm inviting you and hope to see you on our workshops on RTC on conference. It will be happening in October, and there is a discount code right now that you can buy tickets, so make sure to, if you're interested, to buy it now. And we'll try to show you even more in-depth look into how you can process video with other models and how you can optimize them even more so. So I hope to see you on RTC on workshops, and that's everything from me. Thank you.